everyone, thank you for joining us for today's webinar. I'm Indu from MATLAB Helper, and MATLAB Helper is a leading provider of MATLAB service. Today we are presenting a webinar on image enhancement with MATLAB hosted by me as well as Sushma. Just a little housekeeping before we get started. If you have any queries during the webinar, we do have time for questions at the end, that means in the interactive section. So in this webinar, we'll demonstrate a few methods of image enhancement first and then the applications of image enhancement. So without further ado, we'll just brush up all the basic concepts of image enhancement first. Basic methods of image enhancement are morphological operators, histogram equalization, Wiener filter, linear contrast adjustment, median filtering, unsharp mask filtering, contrast limited adaptive histogram equalization, decorrelation stretch. So in this webinar, we'll be explaining enhancement methods in a brief way. First of all, let me start with morphological operators. Morphology is a set of operations that process images based on shapes. Here, each pixel in the image is adjusted based on the value of other pixels in its neighborhood. We have few morphological operators such as I am open, I am closed, strel, etc. And these are mainly used to analyze the image or an object. For example, consider an image of the coins on the surface which is uneven. So here we can find few parameters such as number of coins on the surface and the area of each coin, etc. with the help of morphological operators. Let me explain you all this with an example. So first let me read the image which I have shown you before. For that I'll be using the command imread, I equal to imread of coins.png, and let me just show you that image first. Show of I'll be running this program. As you can see, this is the picture I want to analyze using morphological operators. Let me show you how we analyze. So as you can see in the picture, background is of not same color. So first let me make the uniform background color. Make uniform background. So yeah, for that we'll be using the command strel of disk, 35. So strel is the command used to represent the flat structure element. A flat structure element. And so how do we actually make the background a same color? Let me just open the picture of background first now. Background equal to I open of I comma sc. If we subtract the original image from this background image, we'll get a uniform background. So I2 equal to I minus background. And let me show you the uniform image. I am show of I2. I'll run this command now. Okay, it is strel. Let me run this program again. So this is the picture which have a uniform background. So now it is easy for us to calculate or analyze any image. In this image, as you can see, we cannot differentiate exactly between coins and the background. So let me just differentiate them by contrasting. So to improve contrast, we'll use a command imadjust. But imadjust command can be only used for grayscale images. But now my image is an RGB image. So I'll just first convert into a grayscale image, RGB to gray of I2. Okay, then I'll contrast. I am adjust of I4. Let me show you the contrasted image. I am show of I3. So this is the contrasted one. To contrast image, I'll run this program now. So this is the contrasted one. As you can see, we can differentiate between coins and the background. So to perform any operation, we need to convert an image into its binary version. So we can convert image into its binary version using the command imbinarize. To convert into binary version, BW equal to imbinarize of I3, and to eliminate background noise, we'll be using the command bw area open off. BW equal to BW area open off BW comma 50. So with this command, we'll remove all the pixels which have fewer than 50 pixels. So in this way, we'll be converting any image into its binary form. Now we can do some simple operations on the image. Let me show you how. For example, I want to identify number of objects in the image. To identify number of objects. Here my object is a coin. So cc equal to bw comp of bw comma 4. So this command is used to find all the connected components in the binary image. So cc dot num objects. With this we can count number of objects. I'll run this program now. As you can see, the number of coins in the image are 10 apart from the merged ones. So in this way we can count the number of objects. Apart from this, we can also identify area of each coin or calculate area of each coin. Let me show you how. Calculate area of coin. For example, if I just want to calculate area of a fifth coin, so first we just need to know what is the fifth coin, right? So for that, cc equal to false of size of bw. With this command, I'm just making all the coins as false. Now let me just only make of my fifth coin as true. So coin of cc dot pixel idx list of 5 equal to true. And I'll show you the image now. I am show of coin. I'll run this program now. As you can see, this is my fifth coin and I want to calculate area of my fifth coin. Let me show you how. For example, I'm storing the data of coins in coin data, region props of cc comma basic. Here region props return specified properties for each object. So coin areas equal to coin data dot area. Then I want to calculate area of my fifth coin. So coin underscore area of 5. This will display the area of fifth coin. I'll run this program now. So area of my fifth coin is 1940. So this is how we'll perform morphological operators on any image, and we can analyze the image in a simple way. Next image enhancement method is Wiener filter. Wiener deconvolution is used to deblur the images. Now I'll be explaining you the algorithm of Wiener filter with an example. First of all, let us create a blurred image, then deblur the same image using Wiener filter. For that purpose, read the original image into iOriginal using the command imread of flower.jpg. We have to create a point spread function by using fspecial. Point spread function describes the response of an imaging system to a point source. When a point spread function convolved with an original image, blurred image is produced. So we'll be using the fspecial function, fspecial of motion, 21, 11. Here, the 21 represents the length of the motion and 11 specifies the angle of motion. Now the original image I is converted to double precision by using the command im to double. So I double equal to im to double of I original The reason to convert it into double precision is basically MATLAB has two ways of representing image. Images can be represented as a double precision numbers in the range 0 to 1. Images can also be represented as integer data classes, especially unitate, in which case the values are integers of 0, 1, 2 and so on to 55. Sometimes operations on images are easier when the images are represented in floating point. Hence, we are converting the image into double precision image. Now, the image is convolved with point spread function using the command imfilter, and the blurred images is stored in blurred equal to imfilter filter of I double comma psf comma conf comma circular Here conf specifies imfilter performs multidimensional filter using convolution, and circular specifies input array values outside the bounds of the array are computed by implicitly assuming the input array is periodic. Now we can restore the blurred image by using the deconf WNR function. So WNR equal to deconf WNR of blurred comma psf. This command deconvolves the image using Wiener filter algorithm. Now let me put a command im show of WNR. Now let me run this program. So as you can see, this is the original image and this is the blurred image and this is the deblurred image we got using Wiener filter. So this is how Wiener filter is applied to deblur the images. The enhancement method is contrast limited adaptive histogram equalization. Basically, adaptive histogram equalization is a computer image processing technique used to improve contrast in images. Unlike histogram equalization, adaptive method computes several histograms, each corresponding to a distinct section of the image. Adaptive histogram equalization has a tendency to over-amplify noise in relatively homogeneous regions of an image. In order to prevent this limitation, contrast-limited adaptive histogram equalization technique will be used. I'll be explaining you contrast-limited histogram equalization on colored image with an example. Image using the command imread. I imread of moon.jpg. Then convert this image into the label matrix using the command rgb to lab. lab equal to rgb to lab of the image I. Now scale values to the range expected by adapt this t equal function. So L equal to lab of 1/100. Now perform the contrast limited adaptive histogram equalization operation on the label matrix L. L equal to adapt this t eq of L comma num tiles comma 8,8 comma clip limit comma 0.005. Now scale back the label matrix to the original matrix. That means LAB of colon comma 1 equal to L into 100. Now convert the label matrix to RGB image. J equal to LAB to RGB of lab. Now display the image using the command imshow. I'll be running this program now. As you can see, this is the original image on left side and contrasted image on right side. So this is how contrast limited adaptive histogram equalization function is performed to increase the contrast of an image. The other enhancement method is decorrelation stretch. Decorrelation stretching enhances the color separation of an image. Decor stretch function is used to apply decorrelation stretching in MATLAB. The original color values of the image are mapped to a new set of color values with a wider range. Hence, the primary purpose of decorrelation stretch is visual enhancement. By explaining you the algorithm of decorrelation stretch by enhancing the image of a bird. First, read the image using the command imread of bird.jpg. Then apply the decorrelation stretching for the image I. Decor stretch of I comma tall comma 0.01. Then I'll be displaying the image. I'll run this program now. As you can see, this is the original image and this is the enhanced image in the right. This is how decorrelation stretch is performed in MATLAB. So guys, you can be a brand representative of MATLAB Helper. For that purpose, you just need to follow a few steps. So now let us just look over that.
Let's begin with our application. Once the application starts enhancement window which will be shown to the user, named as Medical Image Enhancement MATLAB Helper. Here the user must first load the image using the Load Image button. I will show an example image of an X-ray first. Now choose the X-ray over here, which is IMG1, and click Open. Now that the image is seen on the axis, let's move to the next step of adding noise. Click Add Noise button. This is the second window showing the input image, and the user can choose the type of noise to be added to this image. These here are a few commonly known noise present in medical images: salt and pepper noise, speckle, Gaussian, and Poisson. For now, I will be choosing salt and pepper noise and click Noisy Image. Now the noise gets added to the input image, and you can see it over here. The image that you see now is how a medical image looks when errors caused by humans or machine affect the scan. These kind of scans must be enhanced by filtering of noise. Now press the filter button. When the filter button is pressed, the app filters the image based on the type of noise affecting it. For the salt and pepper as well as Poisson noise, adaptive median filter algorithm is implemented, which shows great results, as you can see over here. The threshold over here for the salt and pepper noise is 0.3. That is approximately 30% of the image is corrupted, and yet we get back the original image as clear as this. Now the scan can be further enhanced. The resultant filter image must be enhanced so that we can get a clearer view of the bones and the connections to each other. For enhancement, you can either press Enhance Scan button or Enhancement of Iris. As it may be obvious, Enhance Scan is for X-ray, MRIs, and other such scans, while Enhance Iris button is for iris image only, which results in being able to see a clearer view of the features of the iris. Since this is an X-ray of a hand, press Enhance Scan. As you can see now, the resultant image is shown over here with a clearer view of the connections between the bones, while in the filtered image it is not that clear as in the enhanced image. This kind of enhancement is done by morphological operations such as open in this case, and similarly enhancement can also be done on iris as well. Let me show that to you. Now let's see for the iris image. It's the same steps as we did for X-ray. First click on Load Image and choose an image which is the iris image, in this case IMG2, and click Open. You will be able to see the iris image in the axis. Following that, click Add Noise button. Choose the type of noise you want to add over here in the drop-down box. Let me show you how the image changes with each type of noise. Salt and pepper, you can see black and white dots on the image. Speckle noise is where you can see granular noise added to the image. Gaussian and Poisson. For this particular example, let's go with Gaussian noise. Now that we have added the noise to the image, let's move on to the next step, which is filtering. Now that we have got the filtered image, you can see that the noise has been removed in the resultant image. Over here, since this is the iris scan, click on Enhance Iris so that we can see a clearer view of the features in the iris. Over here, now we can see the fine features of the iris, and this is the result of enhancement of iris. Now that we have shown two examples, let's now see how the algorithms work and how to code them. Images are actually comprised of pixels which are represented by numericals in a matrix. You can consider a color image as a 3D matrix, while a grayscale image can be considered a 2D matrix with values ranging from 0 to 255. So you can see that the numbers represent each pixel, and similarly for our consideration, we are picking out each pixel and are considering them individually. Let us now look into adaptive median filter algorithm. When we are considering the algorithm to decide a value of a pixel, it is necessary for us to consider its neighbors. So for that, we need to look into what padding function is. We pad values or pixels to the image. What it does is it makes a boundary pixel layer around the image. If you consider 1, 2, 3, 4 as the image values, then the zeros surrounding that particular matrix is the padded values. Without this, the results of pixels in the edges can't be determined properly, because in this case we are determining the value of the pixel by considering the values of its neighbors. You can pad in different ways. Zero padding, as in this case shown in the image, can be done, or reflection padding, wherein the edges are reflected onto the padded layer. Like instead of 0, which is above 1, there would be a 1. Similarly, a 2 above the pixel with value 2. It would reflect the values at the edges. And the other necessary step that you need to consider later is windowing. Windowing and masking, it can be a 3x3 matrix, 5x5, or 7x7. Since we are doing an adaptive median filter algorithm, we are deciding and adapting whether the median should be found out for a 3x3 matrix, 5x5 matrix, or a 7x7 matrix. Over here, you can see the highlighted area for the center of kernel or the center pixel. Surrounding 8 pixels determine the value of the one present in the center of the kernel. Similarly, you will have a 5x5 matrix as well as a 7x7. Now let's consider the algorithm for adaptive median filter. The notations that you must remember are Z minimum, which is the minimum of the windowing area. Consider SXY as the area we will be considering. If it is a 3x3 matrix, then SXY would be comprised of 9 elements, and SXY for a 5x5 window will have 25 elements, and for a 7x7 window will have 49 elements. So Z minimum is the minimum of that whole window. Z maximum, maximum gray level value in SXY. Z median, median of grayscale levels in SXY. zxy, gray level coordinates x and y, meaning the center pixel. Smax, maximum allowed size of sxy. As we already talked about, the size of the windows would be 3, 5 and 7, which would increment in odd numbers, and Smax for our case is 7. Now let's look into our algorithm. For level A, you should find out whether the Z median is greater than the minimum and less than the maximum. If that is true, as the algorithm goes, you should go to level B. Else, the size of the window should be increased. If the window size is less than Smax, then level A should be repeated. If the window size is greater than Smax or equal to Smax, then the output of that pixel is the current pixel itself, zxy. Moving on to the next level, level B, where we find out whether the center pixel zxy is greater than the minimum zmin as well as less than the maximum zmax. When this is true, then we can say that zxy is not an impulse noise and is noise free, so it retains its value. Else, the output would be Z median. Now let's look at the flowchart of the same. It's the same if condition. For level A, we are finding out whether the Z median is in between Z min and Z max. If that is true, we will further find out if zxy is between Z minimum and Z max. If that is true as well, then the noise is not present in that particular pixel and we retain its value. Else, Z median is given out as the output. If Z median does not lie between Z min and Z max, but is equal to the Z min or Z max, then the window size must be increased. So for the window size to increase, we should find out whether the present window size is equal to the maximum allowed window size Smax. If yes, then the output should be the median of that particular window, Z median. Else, window size is increased by h equal to h plus 2, that is 3 becomes 5, and thereby increase the window size in odd numbers. In order to open AppDesigner, first open MATLAB, go to the plus icon present in the menu under the home section, click on App, then AppDesigner. Once the AppDesigner is open, you can see the component library on your left side and component browser as well as component properties on your right side. In the middle is the design canvas to create the look of your application. First, save this application as Image Enhance. Now that you have saved the application, to create the visual components, just drag and drop the components into the design canvas. Once you click on the component, you'll be able to alter the features by using the properties on your right hand side. You can have title, labels, appearance, font. You can choose the type of font you want, size, Bold as well as italic options are also available. Once the design part is done, you can see the AppDesigner automatically generates object-oriented code that specify your app design and layout. So the code for creating application GUI need not be written by you, but app behavior is another picture. When components are added to the design canvas, you can see that they are automatically added to the component browser as well. Now click on any action component like a button, in this case, when you go to callbacks, add button pushed function callback, you will be able to edit your behavioral function over here. So the app behavior can be controlled by using these functions and writing it over here. The rest of the code cannot be altered, but only the behavior of a particular property or component can be changed by you. Now that you have a general idea of how to use AppDesigner, let's design our first panel. Now that we have a clean canvas, drag and drop a panel, clear panel, and you can also change its color. The background color, I'll change it to a bit dark. Now that that is done, drag and drop label where we will be writing the title of our application and an edit field where we will be adding the text we want to display over here permanently. Let me paste the text I need from the notepad. Alignment to center, bold. It should not be editable, but it should be enabled so that it can be viewed. And our title will be Medical Image Enhancement with MATLAB Helper. Bold, increase the size. Move it to the center. Drag and drop the next panel wherein all the necessary steps will be done later. Let's call the first panel as menu panel. Now drag and drop the axis. This is where you'll be able to view the image. I'm naming it as image. There will be no coordinates. Changing it into box. Color is white. And now that that is done, drag and drop two buttons. You can always copy paste. Let the first button be load image and the second button as add noise. Now that we are done with the first panel, similarly we'll be creating the second and third panel, which is noisy panel as well as the comparison panel. Similar to how we had created the menu panel, I have created the noise panel as well as the comparison panel, where the input and resultant image are compared with enhance scan and enhance iris button present. And in the noise panel, you can see the image, choose the type of noise to be added, and get the noisy image and filter the noisy image by clicking the filter button. Now that the visual components of the GUI are ready, let's move on to the code view and how to get the behavioral application code over here. Click on the component you want to call back, that is load image for us, callbacks, and click the button. Now that the callback is done, you can start typing the behavior of that button. For the load image button, choose file name and path name and use the function UI get file with a dot there. And write location of file. Now that you know the file name as well as the path name, create a variable called full path and save it to it. Now that we have the location of the image, you can string concatenate the path name as well as the file name and save it to our input image. And that can be redefined again to get our input image by reading imRead. Now that the image is read, use imShow to view the image. App.inputImage in the axis. That is usually defined as app.UI axis. Now that this is done, let's go back to the design view and do a callback for add noise function. Once you click the add noise button, you want to move from the menu panel to the noise panel. So app.menu panel dot visible is equal to off. Now that with that statement, you're making sure the menu panel is not visible, and you're gonna make sure the noise panel is visible. Now that you have the menu panel off and the noise panel on, use IMShow to show the input image. And check out the name of the UI axis. So this should be named as UI axis 2. The next thing to be done in this here is when noise is added, the image should be changed from RGB to gray. So app.input image should be equal to RGB to gray of app.input image. Now this is done. Over here you have two buttons, noisy image and filter. Now for the noisy image button, since the axis is already present and the switch keys is already there, and that variable is known as app.noise, where the values can be salt and pepper, speckle, Gaussian and Poisson. We are creating a switch case. Switch app.noise.value case salt and pepper, then app.noisy image is equal to we are giving it a threshold of 0.3. Case. and the second one is speckle. Let's copy paste. Gaussian and Poisson. Now that we are done with the addition of noise to the image, let's go back to the design view and see the next button, which is filter. Now that you have pressed the filter button, the noise panel as well as the menu panel should be off, while the comparison panel visibility should be turned on, similar to how we did for the add noise button. Now create a switch case wherein an appropriate filter function is utilized to filter out the type of noise present in it. For the case of salt and pepper, as well as Poisson, we will be using adaptive median filter. So define an image called app.filtered image to be equal to adaptive median filter function, call it, and give the parameter as app.noisy image. But before that, since we are implementing adaptive median filter, app.noisy image must be padded. Pad array function, where you first give the input as the image, pad size, and the method. Over here, the input image is app.noisy image, while the pad size is 1 space 1, where we are only adding 1 on each side, and the method as both. we are using an inbuilt median filter with a window size of 3x3. I am show to view the image. The noisy image in axis 3 and the filtered image in axis 3b. Now that the filter button is done, let's view the components in comparison panel. Turn the visibility to on, noise panel visibility to off. Design view. You have two buttons, which is Enhance Scan and Enhance Iris. Go to callback. When the Enhance Scan button is pressed, we will do enhancement operation on the scan, as mentioned before. For that, let's define structural element SE, which is a disk with radius of 15 pixels. STREL object represents a flat morphological structuring element, which is essential part of morphological dilation and erosion operations. We are using morphological operation, that is a combination of erosion and dilation at the same order, which is open operator, to define the background. Enhancement is done by subtracting the background from the filtered image. Define enhance image equal to image adjust, which is contrast adjustment done on I2. We have enhanced the scan. For enhancement of iris, a simple histogram equalization is more than enough, since we have already enhanced it by noise removal. Now, all the buttons and action components are defined. Let's look into our user-defined function adaptive median filter. Since the code is huge for adaptive median filter, I've already written it. Let's go through it together. Firstly, the function must be defined in methods with the access being public or private. Over here it is public. The function must have initial parameter as app followed by other input parameters, I, which is an image, and the output is an image named output. The size of image is taken into variables m and n, and the output variable is made into an image of the same size consisting of zeros. A temporary variable j is defined on which all the operations are performed. You are going to assign all the values of I to j so that you can perform the operations on j. For the loop, it traverses through each pixel in the image by going from I 1 to m and j 1 to n. Over here, h is equal to 3, making sure that the initial window size is a 3x3 matrix. Smax refers to the maximum allowed window size, which is a 7x7 matrix. A is a variable defined for increment operations only, while f is a flag defined to decide if we should continue with the while loop or exit the while loop. Over here, xmin, xmax, ymin and ymax are defined so that we get 3x3, 5x5 and 7x7 windows for the particular center pixels. The temporary variable defined here will be the matrix window we will be considering, and for that we will be finding the minimum, maximum, median, as well as the current pixel xy, which is also the center pixel. Now let's move on to the logic, wherein we are finding out whether the Z median lies between Z minimum and Z max. If that is true, we'll move on to the level B, where we see whether ZXY lies between Z minimum and Z max. If that is true, then we define that ZXY is not an impulse noise since it is not equal to Z minimum or Z max. Hence, the output is equal to ZXY, which is its current value itself. If ZXY is equal to Z min or Z max, it is a noise, and hence it should be replaced by Z median, which is not a noise in this case. If the Z median itself is equal to Z minimum or Z max, then the window size must be increased. Hence we are giving h is equal to h plus 2, because h was initially 3. By increasing it by 2, we are making it into a 5 cross 5 window, and thereby 7 cross 7. Now that the logic is done, we should check whether h exceeds the S max, meaning even for a 7 cross 7 matrix, the median is also an impulse noise. Then we retain the value as it is and give the flag as -1, making sure you move out of the loop. If the size is less than S max, then Z median is assigned to the output, and A is equal to A plus 1, which is there for incrementation of the window size. And the output I, j is assigned with j of I, j, which will either be ZXY or Z median according to our logic. Now that we have come to the end of our webinar, let us quickly see the topics covered. Morphological operators, Wiener filter, contrast limited adaptive histogram equalization, decorrelation stretch are a few algorithms which were discussed with the help of an example. And we also learned how to create MATLAB application of enhancement of medical images, which made use of adaptive median filter and histogram equalization algorithms, in addition to a few already discussed algorithms. For any doubts, please do attend our live interactive session. Now that you have seen a few applications of image processing, what other applications and uses of image processing can you think of?